Hello, in this video I'll be solving problem 1.40 of classical mechanics. 1.40 reads, a cannon shoots a ball at an angle theta above the horizontal ground. Neglecting air resistance, use Newton's second law to find the ball's position as a function of time. Use axes with x measured horizontally and y vertically. Newton's second law is force is equal to mass times acceleration. A good note is to always start with a drawing for these types of problems. So I'll draw our x and y axes out, where our x is considered our horizontal ground that the angle of our ball is relative to. So I'll draw the projectile, the trajectory of our ball, at an angle theta above our horizontal x-axis. To begin, force is equal to ma, and a is a vector, which can be split up into an x and y component. So it's equal to m times ax plus ay. And we want to consider all of the forces that are acting on our ball as it flies through the air. And since there's no air resistance, the only force is gravity. So it affects the ball in a negative y hat direction, directly down, if we consider up as our positive y-axis direction. So force is equal to negative mg y hat, which we can write out as equal to our x and y components, negative mg y hat. Now we want to find the ball's position as a function of time. So we need to solve for the ball's x of t and the ball's y of t, which we can find by working backwards from acceleration in relative to x and relative to y. Now I hope that you understand, and I kind of need you to understand that a is equal to the second derivative of position, acceleration is equal to the second derivative of position, and velocity is the first derivative of position as well. Those are very simple things, and it's as consistent as understanding sine squared theta plus cosine squared theta is equal to 1. Those are to be expected in this video, as it will just take too long to explain every time I bring those up. So I will write out that m times ax plus ay is actually equal to m x double dot plus y double dot. And these are equal to negative mg y hat. We want to solve for position functions for y and x. So I will first solve for x. So I'll separate our function into mx double dot is equal to 0, because there are no forces acting on it in the x-axis direction, since there's no air resistance and just gravity in the negative y hat direction. Which means that when I write out y double dot times m, it's equal to negative mg. So if we want to solve for x first, I will solve for first velocity. So I will write it out as m dv dt is equal to 0. I will get dvx by itself, so I'll divide both sides by m, and then I'll multiply both sides by dt to get dv of x is equal to 0, since the right side's never going to change as it's equal to 0. We integrate both sides, with the left side being integrated from v naught to vt, and to stay consistent, we'll do t is equal to 0 and t is equal to t on the right side. So once we do this integration, we get v of t in the x-axis direction minus v naught is equal to 0, which when getting vx of t by itself, we find that it's equal to v naught. But we have to remember that our ball is being shot at an angle theta relative to the horizontal ground, which when you draw a triangle, it's simply that a sine theta needs to be added to our, cosine theta needs to be added to our v naught to make it relative to x. So we multiply v naught by cosine theta, and that's our velocity function in the x-axis direction. To get the position function, we take the integral again. So I will write out vx of t as dx over dt, and stay consistent, v naught cosine theta on the right side. I will get dx by itself on the left side by multiplying both sides by dt. So I have v naught cosine theta times dt on the right side. Now I will take the integral to get our position function by doing x naught to x of t on the left side, and t is equal to 0 to t of equal to t on the right side. Doing this integral, we get that x of t minus x naught is equal to v naught cosine theta times t. To get x of t by itself, we'll move x naught over to the right side. So x of t is equal to x naught plus v naught cosine theta t times t. And we placed our canon at the origin, so x naught is actually just equal to 0. So it goes away, and our position function in the x-axis direction for x of t is equal to v naught cosine theta t, cosine theta times t. We want to do this again for y, so I will write it out as m dvy over dt is equal to negative mg. Divide both sides by m and multiply both sides by d of t, and we end up with dvy is equal to negative g dt. And if we integrate both sides like we did to the left, where it's v naught to vt and t is equal to 0 to t, we end up with vy of t minus v naught is equal to negative gt. Get vy of t to the left by itself, and we have that vy of t is equal to v naught minus gt, but we can't actually write that because we want v naught to be multiplied by sine theta, just as we did for the left side. So it's v naught sine theta minus gt, and that's our velocity for the y-axis direction. Of course, we want to take our our integral one more time to get our position function. So I'll write it out as dy over dt is equal to v naught sine theta minus gt. Multiply both sides by d of t. We get dy is equal to v naught sine theta minus gt times dt. Take the integral of both sides, as we did for the left side up there, which is y naught, y of t is equal to 0, and t. And we get that y of t minus y naught is equal to v naught sine theta times t minus 1/2 gt squared. And y naught is equal to 0, so just write that as 0. So y of t is v naught sine theta times t minus 1/2 gt squared. And we want our ball's position as a function of time, which we will use r of t to represent. And r of t is, when squared, equal to x squared plus y squared. And we have these two position functions right above us. So x squared is actually just v naught squared cosine theta squared times t squared. And y of t is a little more complicated since it's got two sort of things being subtracted, or some sort of function being done on both of them. So we have to write it out just to make sure that we're clear and we don't mess anything up. So v naught sine theta times t, minus 1/2 gt squared. Squared is just multiplying it by itself. Which ends up equaling v naught squared sine squared theta t squared minus 1/2 v naught g sine theta t cubed minus, again, 1/2 v naught g sine theta t cubed plus 1/4 g squared t to the 4th. We plug these back in for our r of t function. So our ball's position as a function of time is equal to v naught squared cosine theta squared times t squared plus v naught squared sine squared theta times t squared. And we are going to combine like terms up here to get just -1 v naught g sine theta times t cubed plus r 1/4 g squared t to the 4th. So that is our ball's position as a function of time. We are now done with part A. Well, no. We have one more thing that we can do, which is, if you recall, cosine squared theta plus sine squared theta is equal to 1. So we can actually simplify this down a bit more. As we can find here, sine squared theta plus cosine squared theta, and they have like terms here, 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 and here. So we can write out r squared of t is equal to v naught squared times t squared times 1. Oh, that's way too much. Minus r v naught g sine theta times t cubed plus 1/4 g squared t to the 4th. And that will be our final form for our ball's position as a function of t, as a function of time. Now, part B wants us to let r of t denote the ball's distance from the cannon. So r of t is just the ball's position as a function of time, like as we described before. And it wants us to find what the largest possible value of theta if r of t is to increase throughout the ball's flight. Now what this means, and this can be described quite easily, is that it wants us to let r of t constantly increase throughout the path that the ball takes while in flight. So I'll show two different instances where theta makes sure that r of t does not increase. So r of t decreases will be on the left and increases will be on the right. Now r of t describes the position as it gets like further away. So if we just have the trajectory of a ball fly this way, r of t at time this point is here, so this is r of t. Later r of t is here, and later r of t is all the way out here. So you can see that this r of t is smaller than this r of t. So r of t is actually increasing constantly throughout this path of flight. So if I draw this again, this is t actually. I'll just have that be our r of t value. No, you can't do that. But this is just our x and y flight axes. So x, y. This is just denoting our path. So on the left side, it's r of t decreasing, and this is when it kind of just peaks like that, like a parabola. So you can see that r of t is increasing, increasing, but then it starts to get shorter again compared to here, compared to like this line. So r of t is shorter down here than it is up there, so r of t decreases over the time of the flight. But as I drew before, which is just sort of like a half ellipse, r of t is black still. R of t is increasing constantly over the time of flight. And that's what we want. Now, what we ended up with is a bit of a quadratic equation. So basically what we want is R of t to, for all of t, for all of the t values, for all of time, to be greater than 0. So it needs to be positive, and that means that it's increasing, and that only happens when it's also not constant. So we can write this out if we first go back to our r squared t equation. I'll write this out one more time. We have r squared of t is equal to v naught squared times t squared minus v naught sine theta, or v naught g sine theta t cubed plus 1/4 g squared t to the 4th. Now, for it to be positive and not constant, that means that the derivative of our r squared function with respect to t does not equal 0, and we want it to be positive, so it must also be greater than 0. So basically, v naught, this needs to be, let me write this out properly. This, when you take the derivative with respect to t, must be greater than 0 and not equal to 0. So if we want to write this out as a quadratic formula, quadratic equation, we can actually just pull out a t, since a quadratic equation is a t squared plus b t plus c. We actually almost have this with our formula, and we can do this by just pulling out a t. So t times v naught squared, or not just a t, by pulling out t squared. So v naught squared without the t squared is our c, as you can see. Sorry. And then we also have minus v naught g sine theta multiplied by t plus 1/4 g squared t squared. So with this, we have our a, b, and c. This is our a, or this is our c. This is our b without the t, and this is our c. Now, we can see that the coefficient of c is actually positive. So, sorry, not c, a. The coefficient of t squared is greater than 0. So when this function is graphed, it's a convex parabola. So when it's graphed, it looks something like this. And we want to look at the vertex of this graph, and we want this to be greater than 0. Now, if it's greater than 0, r squared of t is greater than 0 for all of t, and it's also not constant. So if we just say that f of t, this is our function, we're just coming up with a new function, is equal to a t squared plus bt plus c. And this is just basic algebra, but it's found by first taking the derivative of the function and then finding a critical point and then taking the second derivative to verify it's a minimum. We can find that t minimum from this function is equal to negative b over 2a. This is going to make things a lot faster, and this is going to make this video a lot faster to not explain this. If you want to prove this, just take your own time by taking the derivative of our function t, or f of t. So do the derivative with respect to t, and then taking the second derivative to verify it as a minimum, and you'll find that t min is equal to negative b over 2a. So if we take t min, which is our point right here, we can make sure that it's greater than 0. So if we plug our b and a values in, we find that t min is equal to negative times negative sorry. I'm trying to remember how to do this properly. Okay. We do not have yet our A, B, and C values, and I wrote C twice here, sorry. This is supposed to be A, and this is supposed to be C. To get our A, B, and C values, it's not just pulling out t squared. They're not quite there yet. If you recall, we are supposed to take the derivative with respect to t. So if we take the derivative of respect to t for this function, which we call f of t, so f of t is equal to v naught squared t squared minus, sorry, make sure that this is, oh man, okay, little rewind. F of t is not before it's pulled out. F of t is this equation, as I wrote earlier. I'm sorry, I got a little ahead of myself, I think. So if we take the derivative of f of t with respect to time of f of t, we get 2 v naught times t, sorry, 2 v naught squared times t minus 3 v naught sine theta g, sorry, v naught g sine theta times t squared plus just g squared times t cubed. Since we're bringing down the 4, we get rid of the 1/4. From here, we can pull out t to get our a, b, and c values. So if we pull out t here, we get 2 v naught squared minus 3 v naught g sine theta times t plus g squared t squared. And if we also pull out 2, we can make sure that we're matching our former equation. Because when we're taking the derivative of f of t, our f of t is actually r squared of t. So when we take the d of t of r squared of t, we end up with 2 r of t here. So if we pull out the t, we can cancel out the t. If we pull out the 2, we can cancel out the 2 on both sides. So we end up with r of t is equal to t times 2, sorry, times just v naught squared minus 3/2 v naught g sine theta times t plus 1/2 g squared t squared. Now, we are finally at our a, b, and c. So if we let this be our a, this be our b, and this be our c. Sorry, that was kind of bad. That's even worse, but it's okay. So then we can plug that into t minimum, which is equal to negative b over 2a. So it's equal to negative 3/2 v naught g sine theta t over a times 2. So 2 times 1/2 g squared t squared. We get that t min is actually equal to 3 over 2 v naught sine theta, and there's still a g on the bottom. So if we actually put the v naught sine theta up top, we get 3 v naught sine theta over 2g. Now we plug this back into our function, so r of t min, we get that, it's quite long, so I don't want to write this out here. We get 1/2 g squared times 3v naught sine theta over 2g squared minus 3/2 v naught sine theta v naught g, I always keep forgetting to put that first, sine theta times 3v naught sine theta over 2g plus v naught squared all by itself. And we start multiplying and we start canceling. We can see that the g squared here, well, first we'll multiply. So first we'll square that. So 1/2 g squared times 3, nope, not times 3, times 9 v naught squared sine squared theta over 4 g squared minus 9 over 4 v naught squared sine squared theta. If you multiply this out, plus v naught squared. And if you cancel out the g squared here, you multiply it out a little bit more, we'll see that we actually end up with our r of t min is equal to 9/8 v naught squared sine squared theta minus 9/4 v naught squared sine squared theta plus v naught squared. Now if we pull out v naught squared, then we can actually rewrite it as v naught squared times 1, which is right here. This is just equal to v naught squared times 1 plus our 9/8 minus 9/4 times sine squared theta, since those have the same factors in there, same values. Same variables. When we do this, we get v naught squared times 1 minus 9/8, because this can be made into 18 over 8 for the same bottom denominator, and 9/8 minus 18 over 8 is equal to negative 9/8, so sine squared theta. And remember that we want this to be greater than 0 and not equal to 0, all the way back up here. So we have finally taken the derivative with respect to t of our function at t min. So we finally found this, and we want to make sure that this point is always greater than 0. And if you look at this, the only thing that can make this less than 0 is this negative 9/8 sine squared theta being subtracted from 1. So we actually have that 1 minus 9/8 sine squared theta must be greater than 0. And if we rewrite this all, we get sine squared theta, we get negative, I'll do one step at a time, just to get this like simple. So first we move 1 to the other side. So we have negative 9 over 8 sine squared theta is greater than negative 1. If we multiply both sides by negative 1, we have to invert the greater than symbol. So we end up with 9 over 8 times sine squared theta is less than now positive 1. We multiply both sides by 8, and then we divide both sides by 9 to get sine squared theta by itself. And this doesn't change the symbol anywhere. And that just ends up with an 8 over 9 on the right side, since we first multiplied by 8. So we end up with 8. So we end up with 8 over here, and then we divide both sides by 9, so we end up with 9 over here. And that cancels that out. So we have sine squared theta is less than 8/9, which, take their square root on the right side, or on both sides, and then you multiply both sides by sine of -1. So you're taking the arc sine to the right side. You find, finally, that theta has to be less than around 70.5 degrees. And that is how you solve for what angle it must be. That's the largest possible value of theta if r of t is to increase throughout the ball's flight, since our vertex for our convex parabola is always greater than 0. So theta must be less than 70.5 degrees. One more time. Thank you.